So friends, good morning and welcome to this lecture series of Geomorphology. So if you remember the last class, we are talking something about the drainage pattern, the basic types of drainage pattern, the modified basics, their utilities, and finally we concluded that the drainage pattern of an area, it is very much important to gain preliminary knowledge about this subsurface properties like the lithology, like this porosity, permeability, these slopes, this alluvial cover and something else. Similarly, there are certain cases where this basic type has been modified to certain extent and they are called modified basics, in which there is local changes in the basic pattern. So, irrespective of this drainage type or drainage pattern, the drainage patterns are useful to gaining this subsurface knowledge about the geology, and this also important to say about this climate, the tectonics and this rock exposure. So, many informations can be gathered by closely analyzing the drainage patterns, the drainage characteristics in a time series. So, today we will talk about the river system, how the river works. It erodes these sediments, it erodes the rock materials, it transports with it deposits in particular places like the sinks and the basins, and as we know that this reverse erosion, it is a function of many factors like this reverse velocity, this area, and most probably it is controlled by this base level, and in base level, that means it is the level beyond or below which a river cannot erode its sediments. Similarly, there are local base levels also. So, local base levels, that means if a river which is passing through a lake and is coming to finally these oceans, the lake is said to be this local base level. So, that means base level is that level below which river cannot erode. So, now we will talk about this river system in detail, how they work and how they transport and what are these different geological features, the depositional features, the erosional features, they are associated with the river's journey from this mouth to head. And if you see this figure, this is a complete model of a river basin, and these are the tributaries, and this is the trunk river, and finally these are the distributaries. So, if you see here these tributaries, this main work is to gather water. So, they collect water for this trunk river, and the trunk river is transports up to this mouth or up to this basin, and at the basin, at this junction of this basin, the sediment, due to sediment load and due to change in slope, this river's competency and capacity that decreases, and finally river is divided into many segments, many distributaries, and finally this is delta is formed. And this river's journey, if you see here, it starts from this first order stream, that means at this head of this river basin, and finally it ends at this mouth. So, here there is terminology that is called stream ordering. This stream ordering, that means if we are assigned a river basin to evaluate, so we have to find out which order river basin is it. So, to order a river basin, we have to count the streams, and we have to know these characteristics of streams, how they are joining together and which type of further orders they are converting themselves. So, here if you see this figure in the right hand side, this is written 1, this is written 1. So, these are the first order streams, that means it is the early streams. If you remember when we are talking about this river formation or this channel formation, we are talking something rills, gullies and valleys. So, rills, that is not mappable scale, but gullies are of mappable scale. So, we can say these are these gullies, and you can say this is first order streams, they are of ephemeral nature, not always that they contain water, During rainy season, they transport water from this headwater area to this mainstream, and that is why if you see here two first order streams here, two first order streams they join together and they are converting to a second order stream here. Here this is one first order stream and another first order stream, they are joining together and coming, this is the second order stream. Similarly, here this is a second order stream, because these two first order streams they are missing, this is the second order stream and it is again second order and first order. So, they are coming again, it is second order. Similarly, if two second order, for example, here one second order stream is here, one second order stream is here. So, the result is the third order stream. So, that means here 1 plus 1 equal to 2, but 2 plus 1 equal to 2, but 2 plus 2 equal to 3. So, that means this is the way how these channels or the streams are ordered, and the maximum order or the highest order of a river basin. For example, here if you see this is 2 and 2, that means second order stream and second order stream, this is the third order stream, and here we are creating a third order stream here. So, now one third order stream coming and here one third order stream coming. So, this is the fourth order stream, and the highest order of this stream in this basin, it is assigned the order of this basin. So, that means it is a fourth order drainage basins. So, that means stream ordering, why we do stream ordering and what are the principles of stream ordering we discussed here. So, the stream ordering, there it is, we are following this Horton's hierarchy of stream order. That means lower order of streams are shorter, steeper, drain small area. Now, you see here lower order stream, the first order streams, how much they are influencing, how much area they are influencing, very small area. So, that means first order stream or the lower order streams, they are shorter in length, very small length, and steeper, because they found they are generated at the hilly terrains near this or at the head of these river basins. So, they are smaller in size and steeper in slopes and drain small area, because the slope is a function of area also. So, that means lower the slope, that means higher area a river will or channel will influence, and if it is channels are at the higher slopes like the Piedmonts, like the hilly terrains. So, there are these spots. So, every stream they influence less area. So, that is why smaller streams or lower order streams, they are shorter in length, steeper in slopes and drain a small area. Horton noted that the number of stream in a watershed decreases with increasing order. Here in the important observation by Horton is there, the number of stream is decreasing with increasing order. For example, if this drainage basin we are talking about, see how many first order streams are there, it is more. How many second order streams are there, it is relatively less, and how many third order streams is again relatively less, and fourth order stream it is only one. So, that means we are increasing the stream order, we are decreasing the stream number. So, this is in a regular fashion. When logarithm of the number of streams plotted against a order point lie on a straight line which slope is 45 degree. If you see here this stream order and this is log of streams, it is plotted here, and finally, we are getting a straight line which is slope is 45 degree. So, that means this is a definite mathematical formula they are following, that the number of streams are increasing, the order is decreasing. So, another characteristics of river or the fluvial geomorphology is that is called drainage density. Drainage density, how densely the channels are distributed, how densely the channels are distributed in a given area. So, here drainage density D is defined by L per A or L by A, where D is the drainage density, L is the cumulative length of all order streams, here cumulative length. So, that means if you are talking about this drainage density of this particular area. So, here this total length, that means this plus this plus this. So, that means irrespective of order, here total length of the stream or total area. So, here that means it is a measure of how well or poorly a basin is drained by streams. If the drainage density is high, that means the channels are well distributed or the area is densely channeled. So, that means here we can say this surface drainage network is high as compared to its other part of this area. If area which is showing high drainage density compared to other area, that means the surface of this area is highly channelized. That means number of streams are more, and here this means very closely spaced channels are there. D is higher for steeply sloping, low permeability landscapes, highly vegetated, which promote runoff, gulling and channeling. Here the things to understood, this is the interpretation part. So, here we can say if the drainage density is high, that means these channels are very densely placed. So, that means what is indicating, it is steep slope because we know in this earlier classes when talking about the slopes, steeper slopes they create more drainage, but the length of the drainage are less, the shorter drainage are there, but number of streams will be more. So, steep slopes as the number of streams are more and the length will accumulate, this length will add those numbers. So, finally, we are coming to higher length. So, here it is indicating steep slope, then low permeability. This is another important factor to understand here, low permeability. For example, we are talking about the granitic gneiss megmatites. Here it is low permeability is there. Low permeability means, so that means during raining the surface is filled with water, there will be less percolation downward. Less percolation downwards means all this water that will follow the surface channels. So, that means number of surface channels will be more. So, that means this is indirect indicator of this lithology and slope. So, here it is low permeability landscapes, highly vegetated area which promotes runoff and gulling and channeling. So, these are this interpretation. If you are getting drainage density of certain number, so that means by looking this drainage density we can say what is the subsurface condition, what is the slope condition, whether it is vegetated or not, what is this permeable, it is this channel is flowing on permeable rocks or impermeable rocks, like that. D is lower for low relief, high permeability landscapes, low relief landscapes, that means if it is low relief, that means slope is less. Similarly, high permeability, if high permeability like sandstone or fractured limestone or something whatever may be, so or alluvium, so that means it will percolate, the water will percolate downward. So, once water percolates downward, its surface runoff reduces, and surface runoff reduces, that means it discourages for this stream formation. So, that is why we can say this, looking this drainage density, by analyzing the drainage density we can say about the subsurface geology. So, example here is same drainage basin, within here two equal area, here two part, one is B and another is A, is a rectangle, it is for where drainage density is to be measured of equal area. So, now you see here the channel length will be this much and the area will be this much. Here the channel length, you see we will adding, number of channels are there, we are adding here. So, that means at A the drainage density is less as compared to B. Here area, and we can say here drainage density means it is length per area, and here the length is very less as compared to here. So, that means we are getting a high drainage density and low drainage density in these respective areas. Sandstone, for example, it is more permeable, has low drainage density than granite, which is less permeable, because it is surface runoff is more and subsurface percolation is less in terms of granite, but in sandstone the reverse is true. Then another terminology in fluvial geomorphology is stream frequency. Stream frequency, how frequently we are encountering a stream. It is the number of streams irrespective of its order per unit area, number of streams only. For example, here the stream frequency, that means first order stream 2, second order stream 1. So, here number of stream is 3, but here we are getting the number of stream 1, 2, 3, 4, 5. So, that means stream frequency is the how frequently the streams are, we are getting how frequent streams are there in an area. So, that is stream frequency. It is irrespective of order, number of stream, only the numbers is concerned. So, in a drainage basin there are few points where this river starts its journey to its mouth, and one is the source, the place where river begins, the course, the route the river takes its sea, the tributaries, the small rivers that collects water, and confluence, the point where the tributary join the river, distributary, the channel which distribute river water. So, through which this river starts from source and ends at the river mouth. So, within that it transports, it erodes the sediments from this catchment, it transports to the trunk river, it deposits at the river mouth, and through this river journey it creates many geomorphological features. Some of them are erosional and some of them are depositional. And erosional, mostly the erosional geomorphic features, they are found at the upper reaches of the streams, and because mostly in that part this main work of the river is to erode this topography, and the depositional landscapes mostly it found in the floodplain or where it comes to the slope break from this hilly terrain to plain land where there is a major slope break, it starts depositing sediments here, and in the floodplains it deposits sediment, and in this river mouth it deposits sediments. So, that means mostly these lower slopes or lower reaches of a river, the depositional landscapes are dominating, and in the higher reaches of this river these erosional landscapes are dominating. Then stream competency. Competency means how competent a stream is, for which work, for what. A competency means competence for what? Competence refer to the size of a particle that a river can move or controlled by velocity. So, it is competent to move a particular size of sediment. So, suppose a boulder, a river which is transporting, which can move a boulder, that means its competence is more. It is capable of transporting a boulder. Boulder means a larger size of larger class. Similarly, if it is transporting only, it is capable of transporting clay sized particle, sand sized particle. So, its competency is less. So, that means it is the competency, it is the degree of measure of its force, how river, how powerful a river is, a stream is to transport a particular size of boulder. Then its capacity, river's capacity means it refers to the amount of sediment. Here it is the size of sediment, the competency, and the capacity, it denotes the amount of sediment a river can carry controlled by its volume. So, that means it is the amount of sediment irrespective of its size, the total amount, total volume of sediments it is transporting, and here this competence means the size, the maximum size of this particle a river is transporting. So, now you see here these curves, this one is it is velocity necessary for pick up erosion, here it is velocity for transport, and here it is deposition. So, these curves, this which is separating the erosion, transportation and deposition, it is based on this experimentally derived and from Flume experiment. Flume experiment, if you can remember, we are talking something when we are talking about the modeling, geomorphological modeling in the river system, and how this Flume experiment is carried out to change its slope, change its lithology, to create different types of channels there. Similarly, this experiment or this curve is based on this Flume experiment. So, if coarse and fine particles are mixed, the fine particle will space between this coarse one and are thereby protected, but they also help prevent these coarse grain from moving. Sediment transport by wind has similar competence limit. So, this graph is valid both for fluvial transport both for and for aeolian transport. If you remember, when we are talking something about this aeolian system, the arid zone geomorphology, we have discussed how this wind velocity, it is defines the particle or wind speed and wind velocity is defining the particle size distribution within that aeolian system. Competence is the measure of a stream's ability to transport a certain maximum grain size of sediment. Here the key is maximum grain size of sediments. Maximum grain size means how large particle can be transported by a river. So, competence depends primarily on velocity, although channel shape and degree of setting of sediment particle, amount of suspended load and water temperature can also affect competency. So, these are these parameters that are affecting the stream competency. The first depends upon the primarily velocity. Higher velocity, that means larger boulders can be transported. Also the channel, that depends upon also the channel shape, how the channel shape is. If channel is narrow or channel is wider, and then the shape and degree of setting is also affecting. Degree of setting means this grain size distribution. If distribution is very close, that is well setted, and distribution is range. So, from starting from this clay to boulder, so it is not well setted or poorly setted. So, depends upon the setting of this grain size. Then amount of suspended load, how much suspended load is created from the source, and this water temperature, that water temperature, it is a cold water, it is in hot water and warm water. So, that means these are these parameters, they are defining the stream competency. Capacity, it is a theoretical maximum amount of mass of sediment load that a stream can transport. It is the capacity, maximum amount of mass of sediment. The grain size of the detritus may partly determine how much can be carried, but capacity is primarily a measure of this maximum amount, not grain size of this load. So, it is the maximum amount, not the grain size. Grain size is for competency, but the amount is for capacity. Both dissolved and suspended load in the river water are routinely measured as gauging stations. Any device lowered to the bed of the stream to measure or collect the sediment in motion also deflect the boundary flow conditions and distorted the measurement. So, that is why this bed load data we are getting, it is of not as accurate as we expect. Dissolved load has no detectable effect on stream flow. The concentration average only to 130 ppm. So, these solutions are too dilute to affect the viscosity, turbulence or the density of this river water. Therefore, dissolved load which can represent more than half this total work of this fluvial denudation gets a free ride to sea by rivers. No kinetic energy is required to move it. So, that means the dissolved load has negligible or even if no effect on the river transport. So, whatever the dissolved material, dissolved salt is there, it gets free ride from head to mouth of the river. So, its affect the suspended load, the bed load, but here the bed load, this whatever the data we are getting, it is not of accurate measurement, because as we know this during the high flood time. So, if we are inserting our instrument, it will deflect the system. So, it will be deflected, it will not able to measure it accurately. So, that means whatever the data we are analyzing for sediment transportation, sediment load calculation, river competency, river capacity or whatever may be. So, it is based on this suspended load mostly. Because dissolved load has no effect on this hydraulic geometry of river and bed load defies accurate measurement, the load of a river that is usually measured is the amount of suspended load. The unit of measurement is the dry weight of the sediment per volume of water, or more commonly units such as tons per day of sediment for a specific discharge. So, that means this whatever the data, whatever the calculation, whatever the models that we prepare for this river system in fluvial geomorphology for application purpose, we must always concentrate on the suspended load. Though bed load affect, but as we cannot measure it accurately, so only we assume that this percent of bed load is there or that percent of bed load is there. So, I think we will stop here and we will meet in the next class with his reverse journey, and I stop here. Thank you very much.